Swayam Prabha. Digital India. Educated India.
Okay, so in the last class we were continuing our discussion on receptivity of boundary layer to wall excitation. In the context we looked at the impulse response, that is exciter is placed at the origin, which is vibrating at a pre-defined frequency. As a consequence, you create a kind of a wave train which grows in space, and so this is the corresponding picture of your spatial instability problem, right? So this is what we are doing, and we saw that the disturbances are stronger near the wall, and as you go away they decay. And so this is the one solid line is for the outer point, which we call as the outer maximum, and the dotted line represent the inner maximum of the boundary layer. So this is what we obtained, and we pointed out that there is nothing new learned if you look at far away from the exciter. This is the kind of information that you would have obtained by using spatial stability theory. Only difference you can say is that you did not have to make any assumption whether it belongs to spatial stability or temporal instability problem. All you do here is just simply provide an excitation at a fixed frequency and see what happens correspondingly. And what happens is a very interesting story here, because it has the asymptotic part, that is the waves, those are far away from the location of the exciter, but you have a near field solution in the close vicinity of the exciter itself. This is what the receptivity theory gives you. Stability theory has no clue how to give it. And we notice that the solution does not appear discontinuously. It appears continuously. There is a bit of a upstream penetration, and then it just latches onto the asymptotic part of the solution. So as we are interested now to look at the special attribute of the receptivity theory in explaining the near field response due to this localized wall excitation, then we did talk about the role of essential singularity, that is the point at alpha equal to infinity. And essentially then what you are trying to do is find out what that phi of alpha is when alpha is going to infinity, right? And in the context you do have to revisit Jordan's lemma, which says that the contribution coming from the semicircular arc would be vanishingly small as the radius of the arc goes to infinity. So this is the kind of contour that we talked about in the presence of, let's say, one singularity, or let's say put couple of singularities, and we are talking about this kind of a thing. So basically we have this cut, and we do perform the Bromwich contour integral supplemented by this contour in the upper half, which goes like this. So we have seen what we get in terms of Cauchy's integral formula and theorem. And we are talking about this part, the contribution coming from the semicircular path. Jordan's lemma claims that if phi of alpha has this kind of a structure where the denominator's order is at least 2 degrees higher than the numerator, then this will not contribute anything. So we decided to take a look at that aspect and see if phi of alpha indeed has this property or not, and that's where we began. Also, we noted that there is something more to this whole story, that when you look at the spatial modes along with the group velocity for this particular case of Reynolds number of 1000 and a non-dimensional circular frequency of 0.1, you only get 3 modes. That's it. And that makes us a little worried, because how am I going to explain a very arbitrary disturbances, input disturbances in terms of 3 modes alone? It's impossible task. In that context also, this near field study becomes vital, because what is the absolute near field definition? It's the point itself, and that's where we are applying a delta function. So if I can somehow support a delta function, I know what I can explain anything as a combination of delta functions, right? I can do that, isn't it? Any arbitrary functions could be shown in terms of the distribution of deltas. So that's what we noticed, that in this case, for this specific case we studied, we have 1 unstable mode and 2 stable modes. All 3 modes propagate downstream, and let's then see what we get about the near field, and that was what was the most interesting part that we started. And in studying the near field, we talked about a couple of theorems, Abel and Tauber's theorem, and also the property of Fourier Laplace transform and its duality property. What we find that if we are interested in finding out the response field near the exciter, then it is necessary that I would look at the point alpha going to infinity, because that's the property. That's the property we know of Fourier Laplace transform. Anything that is localized in physical plane, in the transform plane, it's all pervading, and vice versa. So if I am interested in finding out the solution at the immediate neighborhood of the exciter, I would better be looking at the point at infinity. And the point at infinity is interesting, because if I plot it in the alpha or alpha I plane, the point at infinity is basically the circle with the radius going to infinity, right? This is something we must appreciate. So along any such location, I could represent the wave number in terms of the radius and a phase path, which I may call I to the power I theta, or I can write out a shorter notation, call it just simply beta. So beta has beta real and beta imaginary. Okay. Now what you do is you have this expression for alpha in terms of rho and beta. What we can do is we can look at specifically the solution of Gauss-Sommerfeld equation for the specific case when the radius of this arc goes to infinity. That automatically brings in a small parameter epsilon, which is nothing but the reciprocal of the radius. And once I decide to do that, plug that expression alpha is equal to beta by epsilon 1, plug it in to the Gauss-Sommerfeld equation, and I immediately discover the singular perturbation nature of this equation, because the highest derivative is multiplied by the smallest parameter. And this is essentially the issue of all singular perturbation problem, like the original problem proposed by Prandtl himself. There, how did this problem circumvented? We stretched the layer by introducing a new scale, new length scale. So what we had, we discovered the boundary layer, which was thin. So now we are going to do the same thing. We are going to discover the boundary layer of the Gauss-Sommerfeld equation. That is something rather interesting. Well, we are going to solve that equation subject to this set of boundary conditions, 4 boundary conditions required for 4th order Gauss-Sommerfeld equation, 2 at the wall and 2 at the far stream. And in the spectral plane, in the alpha plane, these 4 conditions become this, and positioning of the exciter causes this phi of alpha to be equal to 1. That's the property of a localized function, that it excites all wave numbers with equal intensity and that is the essence of all impulse response studies, right? So if we do that, we're talking about discovering a boundary layer of Orson field equation. So if I am doing that, I should have two layer structure at least. One should be the outer layer, another will be the inner layer. In the outer part, by definition, all the quantities of any order of phi would be of same quantity of order 1, and that brings out the solution to be equal to 0. So this is quite a sort of a revealing solution that we don't have to do much in terms of fixing the outer solution itself. It's a trivial solution. However, the inner solution is quite rich, and to explore what this inner solution is, what you need to do? You need to again stretch it, and that stretching is via the scale delta. So we call that as capital Y as a new independent variable, that is y over delta. And then we discussed in the last class that if I now introduce the primes, with respect to this capital Y, then automatically this 1 over delta and its various power shows up. A fourth derivative will bring us 1 over delta to the power 4, and that's what you are seeing. So what happens is, now you see, this is the story of singular perturbation theory. You'll have to do what is called as matching. Matched asymptote you have to do. You have to see in what way this epsilon 1 and delta appears. For example, we can think of a very, very general characterization. A general characterization would be something like this, that let's say this boundary layer thickness of this Orson field equation delta is very much smaller compared to epsilon 1. If I do that, then immediately I can see what happens. If you just look back in the previous slide, you will see what we are talking about. If delta is very small compared to epsilon, then what happens? These quantities, I could multiply the whole thing by delta to the power 4, right? If I do that, then this will come like this, epsilon 1 to the power 4, and here everything will be multiplied by some power of delta. And since delta is subdominant compared to epsilon 1, it's only this term that will survive. Okay? If that term survives, because everything else goes to 0, so what do you have? Phi 4 equal to 0, then you can show it in terms of a polynomial, right? You will have a plus by plus cy and dy square and so on and so forth. And then what we could do is basically we could use those boundary conditions, those 4 boundary conditions, and see what do we get. And you will find out that the only possible solution is phi inner, phi I should be equal to 1. Well, this of course satisfies the wall boundary condition. That's what we have done, right? However, this will give you a sort of a very funny situation, because your delta is going to be vanishingly small. So you have phi I equal to 1, and then the rest of the places it is 0. So it does not really match smoothly. There is no smooth match between the inner and outer solution. Outer solution is supposed to be 0. So we have 1 and then immediately 0. So that discontinuity is not very mathematically rigorous and correct. We don't accept that as a solution. Now we can look at the other cases. The other case is, for example, delta could be significantly larger compared to epsilon 1. And if I do that and look at that equation, the only solution that is feasible is this, phi I equal to 0. This is a trivial solution. Your outer layer solution, outer solution is 0, inner solution is 0, you have nothing. So this is not something that we do. Now, if you now again take a look at the governing equation, You see that there are other possible pairings. For example, we could have epsilon 1 equal to delta. Then what happens? This is order 1 quantity. This part is order 1 quantity. What about this path? This will go to 0 because this is, I can write it as epsilon 1 square by delta square, that is order 1 times epsilon 1. So, epsilon 1 going to 0, so that will not survive. What about, so from here I will get 2 beta square phi I double prime. What about here? All those terms will disappear, only you will get beta to the power 4 times phi. So, you get this term. You get this as the distinguished limit governing equation when delta equal to epsilon. And now you can see that you have repeated roots, isn't it? You have repeated roots plus beta and minus beta as a characteristic exponent. So, one of the solution would be a e to the power beta y. The second one would be b y into e to the power beta y. Then the third solution is c to the power minus beta y and this. And now you have these 4 constants, capital A, B, C, D, and you can fix those by satisfying the boundary conditions, those boundary conditions that we talked about. You do that and you find that depending on beta real, whether it's positive or negative, you get these 2 solutions which satisfy those 4 boundary conditions. So, if you are on the beta r positive means what? You will be in this path, isn't it? Because alpha is rho times beta. Rho is real, beta real means real positive is this side, beta real negative is on this side. So, on this side you have this kind of a solution, and on the left half plane you have this kind of a solution. Now, in doing singular perturbation theory, what you need to do is exhaust all possible combinations that you can think of. See, for example, I can note some kind of a distinguished limit appearing here, right? This is something like your epsilon 1 cube by delta square. We can investigate that. I will not do it. I will leave it for you to explore and see that they do not produce non-trivial solution. Okay. So, the only distinguished limit that we can talk of is essentially delta equal to epsilon 1, and the solutions are as given here. And that's what the second last point we just now talked about, that we can have this following 2 distinguished limits where delta square equal to epsilon 1 cube or delta square equal to epsilon 1 to the power 4th, and for you to show that this 2 distinguished limit leads to trivial solution. Okay. Now, what have we found out? That's a very interesting thing. We have found out the orthogonal field equation has a boundary layer whose thickness is given by delta, and delta is equal to epsilon 1, and epsilon 1 itself goes to infinity. Now, you know, this is all very nice about talking about mathematics. Physically, what happens? If I try to excite a flow, can I excite any wave number? Think of it physically. Physically, can we excite all wave numbers? What is the wave number related to? Can you relate it somewhat with the energy content? You see what happens. I have a uniform flow. I am creating an excitation. What is the consequence? I am creating a stress field that strains the fluid, and the strain rate is proportional to what? The curvature of the streamlines. And if I create very large wave number, I am creating waves which actually distort very rapidly in small region, and alpha going to infinity, the strain rates are going to go to infinite value. So, mathematically we can talk about alpha going to infinity, but in reality we will have a finite limit on the maximum value of alpha. So, that would also give you some kind of a finite thickness of the boundary layer of the Orson field equation. So, it is not like epsilon 1 going to 0 and delta also going to 0. So, again we have some kind of a discontinuous solution. It is not. It is either of these two branches, and at the end of the boundary layer it is going to go to 0. That is your outer solution is, right. So, aesthetically this is true. Those of you who may have had some exposure to turbulent flows, you may have heard of people talking on Kolmogorov length scale. There also the people tell you the same thing, that you cannot sort of excite any arbitrary length scale, because eventually the strain rate will match to the dissipation will be created via exuding energy as the heat, right. So, that fixes the length scale alpha max. So, here also we are noticing the same thing. It is not turbulent flow, it is a laminar flow, but we are talking about finite energy disturbance. So, we cannot have alpha infinity, we have finite quantity, and the solution is what we are talking about. Now, if we talked about in terms of rho and beta, right. So, if I now switch over back to alpha, this is what those two solutions are. This 7,2 is the solution here, 7,3 is the solution there. So, you have now the expression of phi along this semicircular arc. Life cannot get better than this, because this is what we said. We wanted to investigate if Jordan's lemma is correct. If it is not, what is the contribution? You can very clearly see Jordan's lemma is not necessarily correct, because this you can of course write it in a form of numerator by denominator, but it is not directly evident that Jordan's lemma would be valid. In fact, what we could do is we could evaluate the contribution coming from the semicircular arc, and in doing so you have a task at hand, because your semicircular arc is continuous, but the function is not. We have seen what happens. On this part we have 1 plus alpha y e to the power minus alpha y. On this side 1 minus alpha y into e to the power plus alpha y. So, what happens is there is a kind of a discontinuity at this imaginary axis path. So, to avoid that kind of a problem, what we do is fragment the semicircular arc into 3 parts. The first part is going from real axis to up to a point here. This point P1 and P2 are defined by this small angle epsilon. So, in the limit what we would do, we would make this epsilon go to 0, so that this P1 and P2 will approach P. So, what we would do is we basically would find out the contribution coming from this part, coming from this part, and coming from the middle part. Okay. In the middle part your solution is discontinuous, but you know how to handle it. You take the average of left and right and limit, right, that we are quite aware of what to do. So, basically then we are performing this integral, and on C1, the right segment, we have phi y of alpha given like this, 1 plus alpha y e to the power minus alpha y. On the left part, left half plane, we'll write 1 minus alpha y e to the power plus alpha y. And at the point P, what happens? Well, you'll have to take a limit average of left and right and limit. That you can do it. That we can very clearly see that alpha at the point P is becoming purely imaginary, and that is your I rho, isn't it? So you get this. So you get this part. And this is what I told you. What is this? This is cos of rho y, isn't it? This is cos of rho y. And this is what kind of a function we're talking about? The disturbance which goes zigzags all the way to infinity. It's an artifact of the particular point. And this is something I was telling you about, that this is what is called as the anti-Stokes line. We'll not talk about anti-Stokes line, but let's keep it in mind that we can perform this integral. Although the function may behave a little unphysically, but its contribution can be worked out and we can see what happens. And those 2 points P1 and P2 that we are talking about here, by positioning this is your P1 and this angle is epsilon, and similarly I have another point here P2 and that angle is also epsilon. So we can find out the corresponding value of beta. Okay, on this side your theta is pi by 2 minus epsilon, right? So if I do that, beta 1 can be written as I plus epsilon. And similarly for this point P2, I get beta 2 should be equal to e to the power I pi by 2. There should be a plus sign here, right? There is a mistake. It should be plus. That will work out to I minus epsilon. Okay. So for small values of epsilon, we can fix those phase beta 1 and beta 2, and then we can go ahead and calculate various components. The first component I1 would come from this point to P1. That's what we are doing. So 1 over 2 pi e to the power minus I omega naught t, performing the integral from 0 to beta 1. And this is your value of alpha, 1 plus rho beta y e to the power I beta rho z. And d alpha becomes this. D alpha is nothing but rho times d beta. And then you perform it. It works out like this. It works out like these two expressions with this complex variable z, that is equal x plus iy. That's your I1. And you can calculate the contribution coming from P1, P2, this part. Again, work it out as we saw it. It was cos rho y, and this is what we are going to get. And finally, the contribution coming from P2 to this part, that we are calling as I3, and that would work out in this particular fashion. So you can work it out and see they will be in terms of the complex conjugate of z, that is x minus iy. So it's easy now. You have the expressions for the three contributions coming from three different parts of the semicircular arc. Collate it. Collate it, and this is what you are going to get. This is what we are going to get. We got to remember that we are looking at the specific case when rho goes to infinity, right? And this function, of course, if you try to code it and try to plot it, this will look horrendous because it will show fantastically fast varying phases. However, what we can at least do is try to see what happened to the solution when we go to the point where we are exciting. So that is what? That is at x equal to 0, y equal to 0. We can do that. So if we do that, what do we get? We get an expression like this, psi of x at y equal to 0, it's given like this. This simplifies to this. Now, what you notice that very interestingly enough, that the first and the third term will have associated e to the power minus rho x. Now, if rho goes to infinity, this goes to 0, this goes to 0. So, you know sin x by x is of course the sine function. This is this varies from 1 to 0 and so on and so forth. So, this is bounded. What about this? This is a very interesting function. This is a function that is called a Dirichlet function. You know, there are many approximate way of expressing delta function. Dirichlet function is one such representation. And what you do that in the limit rho going to infinity, this part gives you delta x. So, this is satisfying. This is satisfying. What does it tell us? As a solution, we are not going to talk much about whether they are the right solution or not, but what we could do is we could construct a solution analytically now, and that solution shows that you can recover that delta function excitation, isn't it? That's what we are seeing. So, what is interesting is that if I take a boundary layer and if I excite it at one point, the delta function is supported by the point at infinity, and this is very, very satisfying. This is the property of Fourier Laplace transform. If I am looking at what it is going to be, and that is precisely what we got. And if you now recall the figure that we drew right at the beginning of this class, we saw the solution at inner and outer maximum. And what we saw that the more we come closer, let's go back and then you will see what we are talking about. Okay, I think there is this solution. Let's look at this. This is a similar solution. What you are seeing is a solution which is plotted at 1.2 times delta star. That is pretty much on the outer edges of the boundary layer. But if you keep looking at the lower and lower point, then you would find that this curve will come here and this peak will go higher up. That is what you are seeing, that as y comes close to the wall, your response field peaks up, becomes narrower. That is what we are talking about, representing the solution in terms of Dirichlet function, rho going to infinity. So, you see the beauty of it, that what you saw analytically is also what you recover computationally. This is all from the solution of the Orson field equation. How did we get this solution? By just simply performing the contribution from this point to that point. I mentioned this point, that once we do this Bromwich contour integral, information about everything is embedded there. All those effects of those singularities are there. The effect of this semicircular arc, they are all built in that solution, because phi y of alpha basically gets that. Okay, so now we have crossed a major hurdle. So now let's talk about a little bit about the property of this near field. And here what you are seeing is the solution plotted, response field plotted for the psi as a function of x over delta star for 3 Reynolds number. 400, 1000 and 4000. Why did you choose these 3 numbers? For 400, what do you expect? It's below the RE critical. So the disturbance should be damped. And that's what you are seeing, that this is that 400 solution. It is decaying. Okay, that is that part. What about 1000? 1000 is inside that neutral loop, and you have unstable solution. That is what this solution is. It's growing. And when you go to 4000, what do you have? If you recollect that your beta naught, or let's put it as omega naught, we are doing omega, let's put it like this, and this is your neutral curve, and we are talking about omega equal to 0.1 solution, so it should be something like this. So 400 is somewhere on this side, so that's your 400, R equal to 400, because this is 520, so this is there. 1000 is here, so this is your RE equal to 400, and this is 1000, and 4000 is somewhere here. That is again going to be stable, and in fact that is so far away from the neutral curve that decay rate will be stronger than what you have for 400, and that is what you are seeing, that 4000 solution is here. Okay, so that is what the stability theory tells us. We also verify. What we see though, the near field part of the solution, they all collapse on each other. They do not depend on Reynolds number. Why so? If you recall, it comes from this contribution. And what was the governing equation? If you look at the governing equation that we recovered there, is given by equation 80. Do you see a Reynolds number appearing in that equation? So no wonder. So this is a vindication of what you wanted to do, what you wanted to see, and what you see. This is a self-consistent result by itself. That's why when you perform the Bromwich contour integral numerically, you get the solution. Aha, and this is that reason that your local solution does not depend on Reynolds number. We will talk about it further, because where is this term coming from? Where is this term coming from? To understand where this term is coming from, let's look at the Navier-Stokes equation, the holy grail of fluid mechanics. Everything should be included in your Navier-Stokes equation. So you see, we wanted to find out where from this term comes. So let's look at the Navier-Stokes equation. I have purposely written in terms of stream function and vorticity. Okay, so what happens is, this is the kinematic definition of vorticity, del square psi equal to minus omega. You plug it into your vorticity transport equation. So vorticity transport equation is d omega dt, this is the substantive derivative, should be equal to 1 over Re into del square omega. So if I substitute omega equal to minus del square psi, I get this, right? So what is this equation? Here we have a Laplacian on the left hand side, and here we have a biharmonic, right? Now if I multiply it by Re, then I get this. Then psi biharmonic equation, if I write it in terms of Fourier Laplace transform, what would it be? This will be this. So what you are seeing is very, very revealing, that the local solution for which the governing equation is this comes from the right hand side equal to 0. And that means what? Locally the solution behaves like the flow has Re going to 0. That's it. So that is the nature of your local solution. Local solution is given by the Stokes solution. That's what we call as the Stokes solution, right? RE going to 0. So we are seeing this thing very, very elegantly, that it's not due to some assumption. This is all coming from what we have done, that singular perturbation analysis. The inner solution reduces to the Stokes problem, that is del 4 psi equal to 0. So near field solution is viscosity dominated because RE goes to 0. This is something that we would like to see. And you see, we have already commented on this aspect, that requirement of Jordan's lemma, that phi of alpha should go to 0 for alpha going to infinity. Real flows have a finite cutoff wave number, and this more or less is self-explanatory. Tells you that Sommerfeld equation solutions may not necessarily directly give you that exact formulation that we are talking about, right? Because what happens? We have the solution like this. I forgot. Let's say for alpha real positive, this is like this. So this I can write it as 1 plus alpha y e to the power alpha y. So can we say the denominator's order is more than 2 orders more than the numerator? That's what we are saying, that it does not satisfy the condition of Jordan's lemma. And this was not proven before. This was what we have done it. We have preserved this, and today you are seeing it being presented in front of you, that Sommerfeld equation admits an analytic solution in the limit alpha going to infinity, and once you obtain that, you establish that your phi of alpha does not satisfy Jordan's lemma. That's why I was jokingly saying, calling it as Jordan's dilemma, because when we did not know it, it was a problematic thing, whether to accept it or prove it. And we tried to prove it, we ended up disproving it. So that is the dilemma. So that is what we do. Now let me talk about some side issues, but they are not trivial, they are not unimportant. We have obtained the basic unit process of the flow excitation, that is by using a delta function. Imagine what was the experiment done by Schubauer and Skramstad. They vibrated a ribbon. What is the width of the ribbon? It's not a delta function, it has a finite width. That's why we want to talk about what happens instead of having a delta function if I have a finite width. Now you realize, we realize this, we commented also, that if I have the solution for delta function, I can take a convolution of that solution and I can represent any arbitrary function. So we can do the same thing here. Suppose, say, disturbance source is located at x equal to x naught, then this will be the solution, right? And again I can substitute in linearized Navier-Stokes equation, apply a parallel flow approximation, and behold, I get back the Sommerfeld equation for this phi. So for any point, this is the equation, governing equation remains the same. What I need to do is that take that unit solution where the exciter is at x naught and then integrate over a range of x naught going from x equal to x naught going from x1 to x2. So let's say I have got this impulse response, that's what we shown you so far, those solutions. Then I integrate it over this x naught from x1 to x2. So what are we assuming here? that each and every point is excited with the same amplitude. So, this is like the whole thing going up and down, right. So, that is one way of doing it. Analytically it looks neat, but if I tell you to go ahead and try to do it for the solution of Navier-Stokes equation, you will sweat. Why? Because of those discontinuities at the end of the strip. At the end of the strip you will have 0 and then a finite value, and that will excite all possible alphas, and numerically that is a disaster story. So, what happens is people use different kinds of boundary conditions, excitation for the solution of Navier-Stokes equation, which we will show, but as far as analytical solution or numerical solution via Orr-Sommerfeld equation is concerned, this should be okay. This should be okay because we should be able to do it. What will happen though? You are going to get solutions for each exciter location. I will get some impulse response, and your total solution would be a convolution of all this, right? And we have already familiarized ourselves with group velocity. What happened? How did we get the groups of waves? When two neighboring signals very close to each other interacted constructively and destructively at different locations. Wherever it did a constructive thing, we got the wave packets. You recall that? So, here also same thing will happen. However, what we could also do is the problem that I was talking about, solving Navier-Stokes equation. You may not like to give equal weightage, so you could perhaps multiply some kind of a weight function, give something which may smoothly take it to 0 at the end of the strip and go on. So, that is what one can do. One can multiply by W the weight function, which will be a function of predominantly x naught, but it is defined in the limit x1, x2. So, we could define some function here and can work on it. Now, I told you that for Navier-Stokes equation we do not want this heaving motion of the strip. Instead, we do not do this. We do not want to do this in a Navier-Stokes solution. We want to do something different, where at the end we should have amplitude equal to 0. This is one way of doing it, a Gaussian. And recall, while talking about Fourier Laplace transform, we mentioned a property of Gaussian. It is a Hermitian function. It's a self-reciprocatory. So, what happens is, if I do it in the x space like this, in the alpha space also it will be like this. And we have commented upon against such activity. Why? Because this signal that you are creating is a band limited signal. So, if I am doing this kind of a calculation and this relates to a range of alpha, and if I take if you remember what we talked about earlier on, that alpha I contours are like this, and what about the alpha r contours? They go like this. And now, if I create a Gaussian function over a narrow range, that could only excite a narrow band of alpha r and alpha I. So, but this one, if I take some, suppose this is the range that we are trying to excite, but that would also require, to get the unstable solution, I should be doing it along this frequency. Suppose I do a frequency like this, it does not do anything. So, there is always a worry problem that if I take this, I may be doing something which is not very revealing. So, this is not what one wants to do it. This is what one can do with the help of Orr-Sommerfeld equation. This is what one can do, and one does. What is this? This is called a simultaneous blowing suction strip. What is so good about it? See, if I do it like this, half the part is positive, half the part is negative. The sum is 0. And if I am doing it, if I am creating a kind of a ribbon with this simultaneous blowing suction strip property, then at each and every time, half of the ribbon will act like a source, the other half will act like a sink. So you don't have net added mass. See, this is something also you must ensure that when you are computing, you should not violate any of the conservation principles. And this particular excitation satisfies the conservation of mass at each time, because this is the scenario at any time. What will happen? This whole thing is harmonically fluctuating at a frequency omega naught. So half the cycle this will remain positive, other half it will be negative, and this also will correspondingly flip. But at each and every instant you are going to ensure there is no net mass added. In fact, you would see that in the literature there is lots and lots of article. People talk about zero net mass jets. You know, this is one way of people trying to control the flow, and you want to control a flow like this. You don't want to create a spurious mass generation or create a spurious sink. Instead, you would like to have this. And what is this? In the limit, suppose x1 and x2 approaches 0, what do you get? It is a double delta function, has a very specific name. This is called the doublet, isn't it? So a doublet is nothing but the first derivative of delta function, right? And that's what you see, and that's why delta function doublet behaves like a vector. It has a direction going from source to sink. So these are the kind of things that one can talk about. When it comes to Navier-Stokes solution, you will use this. This one is a little risky. Either you have a very wide ribbon, but as I told you that stability analysis is nice in the context of normal mode analysis, means you study one alpha at a time. But in the receptivity context, we are performing an integral over all alpha. And if these phases are so nearby to each other, they can create a group. So if I am trying to create a monochromatic wave, this is not a good way of doing it, right? Whereas this one is. This one is, because you can really make it a localized one, and you will be creating just a very narrow width function. It will not interact with each other. I will give you some references of work that we had done in the past where we have actually studied this problem. Now, so far what have we done is we have talked about the so-called signal problem. We excited the fluid dynamical system at a frequency omega naught. We also got the response as omega naught. That was our assumption. Suppose we don't make that assumption. So instead of doing a Bromwich contour integral in alpha plane alone, suppose we go and explore the full receptivity analysis. We don't make any assumption of signal problem. Then I will be performing integral also on omega. So I will have two Bromwich contour, one in the alpha plane, one in the omega plane. And then I would write down, let's say, the stream function given in terms of this. Now again we can go back and do all kinds of analysis, but first of all we'll have to specify what is the kind of excitation we are giving, and we'll start our next discussion, tomorrow's discussion starting from this. Okay, so we'll be looking at the full receptivity problem.